Hello everyone, I'm Nosheen Khan from St. Vincent Pallotti College of Engineering and Technology, Nagpur. As from the very first video, you are very well aware with the topic, which is to design power supply using full wave bridge rectifier. Before moving much deeper into the topic, let us see what does the term rectifier means. Rectifier are the circuit that convert the input alternating current into direct current. And if such rectifiers rectify both positive as well as negative pulses of input waveform, they are termed as half or full wave bridge rectifier. Now, there are certain AC voltage parameters which need to be considered under this process. These parameters are peak voltage, RMS voltage, frequency, wave shape, etc. In this video, we will not measure the wave shape, but we will measure the peak voltage, RMS voltage to make the concept more understandable. So, before measuring the values of the components, let us define the above parameters. So, for defining the above parameters practically, I have done simulation in multi-sim software. You can try this simulation in any software you are comfortable with. Here, there are two blocks you can see, XFG1, which is function generator, and XSC1, which is oscilloscope. The box that you are seeing on the left side is the property box of function generator, which is showing the setted values of the generator. Here, I have connected two terminals with oscilloscope and grounded them. Now, after connecting them and running the two blocks, such waveform occurs. You can see that this is a simple sinusoidal waveform. Now here, you'll see the peak voltage is the amplitude of AC sine wave, whereas RMS is nothing but root mean square amplitude. The root mean square amplitude or its value is the effective value of the alternating voltage or current. Now this value gives the same effect with DC steady constant. For example, a bulb is connected to a 5 volt RMS AC supply which shine with the same brightness when connected to a steady 5 volt DC supply. Now frequency. Frequency is nothing but the number of occurrence that an event is repeating itself during per unit time, and it is given by F equals to 1 by T. Its unit is in Hertz. Components that we are using for the model are step-down transformer, diodes, which will act as a rectifier, then we have load, and lastly capacitor. Now this capacitor will act as a filter which will help to reduce the ripple voltage in the output. Here is a simulated model. Now this model you have already seen in video 1, which is without capacitor, that is no capacitor is connected at output with the load. Here the yellow box is called probe in the software which tells the value of the output. Now you'll see here VPP, which is representing ripple voltage, which plays an important role in output waveform. So it should be minimum to get an effective output voltage. Now, as soon as I run this model, I got such waveform. The upper waveform you will see is the ripple voltage that is occurring. As from the yellow box, you can see VPP is now 14.5 volts, which is high in amount. Other values you can also see, VRMS is 10.0 volt, VDC is 8.79 volt, ripple current is 145 milliamperes, and so on. Here, the transformer that we have connected consists of 230 by 12 volt and have 20 turns ratio as seen in earlier video. Now here, rectifier is connected, rectifier of 4 diodes having series 1N4001 and output load. Now ripple factor. What is ripple factor? The pulsating output of a rectifier can be considered to contain a DC component as well as AC component is called as ripples. The basic formula for ripple factor is R equals to 1 by 4 into under root 3 FRC, where F is nothing but frequency as we have discussed earlier, which is 50 Hz standard frequency. R is the resistance. R can be calculated from R equals to V by IC, basic formula, where V is the secondary voltage of transformer, and ripple voltage is nothing but the impure pulsating output voltage.